we had enough unless you want to choose something else. 3x squared plus 2x plus 5 over x squared dx. I need to make a point here, right? So I hope you remember that a over x plus b over x plus c over x, as long as all denominators are the same, can be rewritten as a plus b plus c over x. But also going backwards, if I have a plus b plus c over x, I can write a over x plus b over x plus c over x. This is what I need to do here to simplify it. So first I will write 3x squared over x squared. What do I get? 3x squared over x squared.
3.
Yes, plus 2x over x squared. So I have 1 over x, because when I simplify one of those. And then plus 5 over x squared dx. So I have to perform this step first. It's a must. Okay? So now I'm ready to proceed. Which function prime is 3? Which function prime? Yes, sorry.
Oh, 3x.
That's it. Now careful. Plus 2. We have specific function whose derivative is exactly 1 over x. No guessing. There is a specific function whose derivative is exactly 1 over x. Which function is that?
ln of x.
Very good, but please remember we have to write the absolute value. Awesome. Plus 5. And we discussed this several times. There is a specific function that we differentiate and actually get negative 1 over x squared. So I have to put a negative in front. Which function I differentiate to get 1 over x squared?
Is it just x over, or 1 over x?
Exactly, thank you very much. We made a big case out of this several times this semester. Thank you. Thank you, thank you. So when we differentiate this, because it has minus in front, we will get 1 over x squared. So let me rewrite the function. So 3x plus 2 natural log of the absolute value of x minus 5 over x plus c. Now what I would like to emphasize here before we move on to the next section is indefinite integrals can be checked. The definite ones can be checked only with a calculator, with TI-84. But for this one, we can always check. Always. So let's pick any problem. 7, 14, 10, 28, 39, any of these, so we can check the answer, and I'll show you how to check the answer. So when we have an equation like, let's say, x equals 2, as a solution, right? When, let's say, I don't know, I'm going to make one up. So let's say x squared minus 4 equals 0. I claim that this is a solution. All you have to do is just plug it in. So 4 minus 4 is 0, yes. So exactly the same type of idea, the same idea. So let's choose one of these so I can show you how we check. Which one would you like to choose?
Can we do the last one we just did?
Yes. Good. So we claimed, perfect pick, thank you. We claimed that the integral from 3 plus to 1 over x plus 5 over x squared, don't forget parentheses and outside dx, we claimed that this equals 3x plus 2 natural log of the absolute value of x minus 5 over x plus a constant c. This is our claim. We want to check this. We want to check this statement. Before we do that, I want to refresh your memory on a few things. If I want to solve the equation x minus 2 equals with square root of x minus 2 equals 4, what operator do I apply? What operator do I apply to both sides? So what do we do to both sides, or what procedure, if you don't like the word operator, what procedure we apply to both sides to solve for x?
Square it.
That's it. If I want to solve the equation x cubed equals 8, so the operator here was squared. What operator I apply to both sides here to solve this equation?
Cube.
That's it. So I will apply the cube root operator. Okay. So coming back, you got the idea. So coming back here, the operator we have to apply to both sides is differentiation. Why? Why did I apply power 2 to 1/2? Because they are inverse operations. The square root gets annulled by power 2. Why did I apply the cube root and not the fourth root? Because the fourth root does not annul power 3. The cube root annuls power 3. So what I want you to remember is that differentiation and integration are inverse operations. Same idea with power 2 and power 1/2, power 3 and power 1/3. So I'm going to write that note before we proceed. So please remember, similarly, differentiation and integration are inverse operations. One annuls the other. This annuls this, this annuls this. Okay, so then when I differentiate this side, what happens is this goes away and this goes away, and the left-hand side is 3 plus 2 over x plus 5 over x squared. Now the question is, when I differentiate this side, do I get the same thing? So let's try. So 3x prime, what do I get?
Three.
Good. Plus 2. Natural log x prime, what do I get?
Is it 1 over x?
1 over x. Negative 5 over x squared prime, because remember we know that negative 1 over x prime is 1 over x squared. So I have plus 5 over x squared. What about c prime? How much is c prime?
Let's see.
C prime. A constant prime.
0.
Exactly. So now I'm asking you, does this equal this?
Yes.
Yes. So always indefinite integrals can be checked. How? Differentiating both sides. Good. I think we had enough of this, unless you feel like working on other problems, or can we move on?
We can move on.
Okay. Thank you. So let's move on. So in the next step, next section, 4.2, we are going to talk about areas. Something that I just gave you a little hint of a few minutes ago. So let's take a look. I'm going to choose a very simple function like x squared plus 1. I'm going to choose a very simple interval like 0 to 2. And the requirement here is find the area under f of x on 0, 2. So, perfect. We are going to graph this. When x is 0, I have 1. When x is 2, 2 squared, 4 plus 1 is 5. This is the graph. I know it's quadratic. It has to open up, but I am specifically given 0 to 2, so I have to stay with 0 to 2. Now, can I find the exact area? No, not yet. So we can approximate. Very soon we're going to be able to find the exact, but not in 4.2. Later on in this chapter, we can approximate the area. As I mentioned a few minutes ago, we have to divide the area, divide the interval. So this is 0 and 2. Divide the interval in sub-intervals. So let's start with n is the number of subintervals. Number of subintervals. And let's start with n, let's say, equals 2. And then we look at n equals 4. Okay, so this is the area in question. This is the graph between 0 and 2. The area is what we see here. I don't want to shade it in just yet, but this is the area in question. And I know you're going to ask why. Who cares? And the explanation for now, a simple explanation is, if this is the velocity, like I explained a few minutes ago, if this is the velocity function, finding this area will give us the exact distance. That's why we are looking at the area. Okay. N subintervals, of course, of equal length, or I should say equal width. WIDTH. Okay, good. So I have 2 subintervals. This is what I'm looking at, but I have to use rectangles. And I have several options, and I'm going to show both options here. There is more than 2, but your book presents only 2, so I'm going to stick with 2. There is something called midpoint, and we have many other Simpson's rule and all sorts. But we're going to stick with only 2. So this is the function. This is the interval 0 to 2, of course. And this is our function, which is x squared plus 1. Okay. So here I'm going to show leftmost point. Here I'm going to show the rightmost point. Because we use rectangles, we have to have a height of the rectangle. So This is, of course, 1. The leftmost point means the height is at the left point. So this is the first rectangle. Leftmost point, the height is at the leftmost point. And this is the second rectangle. So we claim that the area here with a leftmost point with 2 subintervals is base, which is 1, times the height, which is f of 0, plus base, which is 1, times the height, which is f of 1. Is this area identical with the area under the graph? No. Is it an underestimate for this particular graph or an overestimate of the actual area? Under or over?
Underestimate.
Of course. Look, I have areas here that are not accounted for. Awesome. Now let's look at the other one with the rightmost point. What does that mean? Base times height. Rectangle. Base times height. A rectangle. So here the area with rightmost point, 2 subintervals will be base 1 times height, f of 1, plus base 1 times height, f of 2. Is this going to be an under or an over?
It's an over.
Of course, by a lot. Because this piece is not under the graph. This piece is not under the graph. So this will be an overestimate. Now, if we have 4 subintervals, I'm just going to show one of them. The 0 to 2. The distance now, the delta x, the distance, the width of each subinterval will be 2 minus 0 over 4 subintervals, which is 2 over 4 or 1/2. 0, 0.5, 1, 1.5. Which one would you want me to illustrate, with the leftmost point or the rightmost point for 4 subintervals? N equals 4 subintervals.
The rightmost point.
Okay, so the area with rightmost point but 4 subintervals. Of course, I shouldn't write equal, I should write approximate because this is no way equal. Good, so approximate. So let's illustrate the rightmost point. Base times height. Base times height. Base times height. Base times height. Base 0.5 times, can anyone give us this height?
F of 0.5.
That's it, awesome. Plus base 0.5 times, can anyone give us this height?
F over 1.
That's it. Plus base, which is 0.5 times, can anyone else give us this height?
F of 1.5.
That's it. Plus finally 0.5, can anyone give us the last one? Times the height of f of,
F of 2.
that's it. Now, here's a question for you. What if I change, so first of all, let me ask this. Do you think of these two? I'm sorry. Do you think of these two? Which one has less error? Which one is a better approximation? This one or this one? The one with 2 or the one with 4?